Hi. In this session, we will be discussing about an important class of graphs called trees. Okay, the trees are the simplest of graphs actually. Okay, so what is a tree? Okay, the definition is very simple. Tree is a connected graph without any circuits. Okay, so basically trees, first of all, it is connected and it will not have any circuits. For example, I have drawn some examples of trees here. You can see that all these graphs are connected here, and this graph do not have a circuit. This graph do not have a circuit. This graph do not have a circuit, but this graph has a circuit. You can see that there are two circuits are there. So this is a circuit, this is a circuit, so this is not a tree. Okay, so what is a tree now? So basically tree is a connected graph without any circuits. That's the only idea you have to understand. It's very simple, and they are the simplest of graphs, and it has a wide variety of applications and can be used to model a wide variety of applications, such as they can, for example, as simple as a family tree, or they can also use to model data structures of computer science. For example, you can see some applications of trees here. Okay, here actually you can actually model the hierarchical structure, organizational structure of a company using trees. Okay, or suppose if you are looking at of your folder of your computer, it may contain many subfolders like this. Or if you go to a web page, okay, the various links which are built inside the web page could be converted like this. So a wide variety of applications could be modeled using trees. Okay, now we will be discussing some important properties of trees now. Okay, very simple properties. By default, by definition, since tree is a connected graph without any circuits, we can definitely say that a tree cannot have loops and parallel edges. It's obvious. Okay, since tree does not have any circuits, it cannot have loops, because if it's a loop, you have a closed walk there, and there are no parallels. If there are parallels also, you will be getting a closed walk there. So a tree cannot have closed walks. So basically that's the idea. So a tree cannot have loops or parallel edges. Okay, and again there is next one, there's an important result is here. So you can just go through the result. There is only one and only one path between any every pair of vertices in tree. Okay, so there can only be exactly one path between any two pair of vertices in a tree. Okay, so how will you prove it? Okay, so first of all, you know that tree is a connected graph without any circuit. So basically you know that tree is a connected graph without any circuits. Okay, so that means between any two vertices there will exist at least one path because it is connected. Okay, and you have to show that there exists exactly one path between any two vertices. Okay, suppose there are two paths between any two vertices. There are two different paths between any two vertices. Okay, so what will happen then? Suppose you take the union of those two paths. What will you get? If you take the union, suppose union, you will get a circuit somewhere. Okay, for example, if you look at this graph, so if you look at this graph here, okay, suppose I have two vertices are there, A and B. Okay, so suppose this is a path between A this way, and this is another path between A and B. So if you take the union, you will be getting a closed walk, or it's called circuit, it's a closed walk. Okay, so it cannot be a tree. Okay, or another case, extreme case, suppose you are thinking about when you need a path from A to E. Suppose you need a path from A to E. Okay, so there is exactly one path between A and B. That's no issue there. Suppose I need exact different. Suppose I'm considering the vertices A and B, A and E. Suppose there are two paths. So you can see that there is a path like this, where A goes to C, C goes to E. Okay, it is going like this. Okay, and you can also construct another path from A to E. Just first I go to A to C, then I go to D, then I'll go to E. Let this, I'll come like this way, I'll come through this way, and I'll come this. So if I take the union of paths, union of these two paths, I can see that I'll be getting this entire portion, and you can see that it contains a circuit. Okay, so if there are two paths, what you have to do? When you take the union, obviously there should be a circuit somewhere there. So that is why if there are two paths between any two vertices, okay, that suppose there are two pair of vertices with where there exists two paths, what will happen? There will exist a circuit when you take the union. Okay, so there cannot exist two paths if the graph is a tree. That's a simple idea, and I have given you an example of tree here. You just think of that again. Okay, suppose if there are two paths, when you take the union, somewhere along those union you will have a circuit. Okay, so in a tree exactly you can have only exactly one path between any two pair of vertices. Okay, so very simple theorem, straightforward theorem. And a connected one is a related one is in a graph. Suppose in a graph you have exactly one and only one path between any two vertices, then it is a tree. So this is the reverse assertion. So you have a graph in which there is exactly one path between any two pair of vertices. Okay, then you have to show that it is a tree. Okay, first of all, the graph is connected. Why? Because between any two pair of vertices you have a path, so it is connected. So that is over. And what extra condition is there for a tree? There should be no circuit. So a tree is a connected graph without any circuit. So we have got that the graph is connected because there is a there is a path within exactly one path within any two pair of vertices. Okay, so it is, first of all, it is connected. Okay, now you have to show that it is a tree, so that you have to show that there are no circuits in the graph. Okay, okay, what is the problem if there is a circuit? Okay, suppose the graph has a circuit. For example, if you look at this graph here, so what is the problem if you have a circuit? What's the issue? So if I take the vertices 8 and 9, exactly one path is there, that is this one. Okay, it's no issue. But if I take these vertices which are there in the circuit, for example, if I'm taking 5 and 9, okay, so can you construct two paths between 5 and 9? First I'll go to 5 to 8, then I'll go from 8 to 9, or I can go from, because of the existence of the circuit, what's the problem? I can go from 5 to 6, I can go to the circuit, then I can go to 6 to 7, then I can come to 7 to 8, then I can go to 8 to 9. Okay, so if there is a circuit, if you there will be at least two vertices which will have more than one path between them. Okay, there for all vertices it not be true, but if there is a circuit, if you look at the vertices of the circuit, we can actually construct two paths between a pair of vertices, some pair of vertices. So if there is a circuit, there exists at least a pair of vertices which have more than one path between them, because you can go through the circuit in two different ways. That's the reason. So if there is a circuit, what will happen? There will be more than one path between. There is a pair of vertices which have more than one path between them. Okay, so that means your assertion that there is a one and only one path will not be true if there is a circuit. That means your graph cannot have a circuit. Okay, so what are we doing here? We have to show that if there is a graph which has exactly one path between any two pair of vertices, it's a tree. Okay, first of all, since any two vertices has a path, it is actually connected. Now to show that it is a tree, you have to show that there is no circuit. Now tell me, what is the issue if there is a circuit? If there is a circuit, you can always find a pair of vertices which have more than one path, because if you look at the geometry of this figure, you will understand why. Because if you take a vertex from uh, which is a part of a circuit, you can always construct an alternate path through that vertex. Okay, so if you are considering 6 also, if you look at this graph, and if you look at the vertex 6 also, you can always connect a different path from 6 to 9, right? You can always connect two paths from 6 to 9. One is through 6 to 5, 5 to 8, and 8 to 9, or from 6 to 2, 2 to 8, and 8 to 9. These are different. Okay, so you can always construct more than one path if the vertex is a part of a circuit. So there cannot be any circuits if this condition is to be satisfied. That is, there exists only one and only one path between any two pair of vertices. So in our graph, it is connected, and moreover, it cannot have circuits. That means it is a tree. Okay, for example, if you look at, you can look at the example of a tree here, and also you can try to think of the same idea in this graph also. Okay, how this was possible. Okay, so if the graph is there is exactly one and only one path between any two pair of vertices, it's a tree. So now you have studied an if and only if condition for being a tree. A tree, in a tree, one condition is that there is exactly one and only one path between any pair of vertices, and reverse process, in a graph, if there is exactly one and only one path between two pair of vertices, it's a tree. So it's a final if condition there. Okay, and moving forward, we can always go for one important proof problem here: the number of edges in a tree. Okay, so the number of edges in a tree is, suppose if a tree has n vertices, the number of edges possible is actually n minus 1. So that's a very important theorem. Okay, so if you have a tree with 10 vertices, it will have maximum 9 edges. Okay, so we will actually prove this result using induction. Okay, I hope you know what is induction. So what is induction? First I will be proving the result for n is equal to 1 maybe. Then I'll assume that the result is true for n is equal to k. Then we'll prove that the result is true for n is equal to k plus 1. Okay, this is actually one form of the many types of induction. This is actually called weak induction. There is also another called a strong induction also. So in that also we'll use the same property. First we'll prove that this result is true for n is equal to 1. Then we'll assume that the result is true for all n is equal to k. All numbers till n is equal to k. Okay, so it is true for n is equal to 2, it is true for n is equal to 3, etc. Up till n is equal to k, we assume that it is true. Then we will prove that the result is also true for n is equal to k plus 1. This is the strong form of induction. Okay, so actually these two forms are equivalent. If you just think both of them are equivalent, I will be using this form to prove this result. Okay, so what we have to prove here? First, you have to show that a tree with n edges, n vertices has n edges, n minus 1 edges. Okay, now this result is actually true for a tree with one vertex. Okay, because if tree with one vertex is basically simply this one, and it has 0 edges, and it is also true for n is equal to 2, right? Because if you draw a tree with two vertices, basically it will be this, because it should be connected, so there should be one edge like this. Okay, so it will have maximum one edge only. So for n is equal to 1, n is equal to 2 also, this result is equal to true. So we'll assume that this result is all true for all vertices till n is equal to k. So this is true for all trees with n is equal to k. Okay, now let us take a tree with k plus 1 vertices. Let us take a tree with k plus 1 vertices. Okay, and if you draw that tree, suppose it has two portions. It's not actually, I'm just drawing two portions here. There will be two, so many things will be here, and actually there will be one edge. So suppose there is an edge between, suppose if you draw a tree like this, and suppose there is an edge between two vertices u and v. Okay, so suppose E is an edge between u and v. Okay, so in this tree, and there can be some other portions here also, some other portions here also. Okay, so there will be some portions like this, and there will be some portions like this. Okay, so if you take a edge from that tree, okay, for example, I'm taking an edge uv, so I'm taking an edge between this u and v, that is our E here. Okay, and you know that there is exactly one path between any two pair of vertices, so exactly this E is the only path between u and v. Okay, why is it so? Because in a tree you know that there is exactly one path between any two vertices. So if you consider this edge EUV, okay, there is exactly this E which is a path between u and v. There is no other path between u and v. Okay, so if I delete this edge E, what will happen? If I delete that edge E, what will happen? This will actually be divided. This tree will actually be divided into two components. If I just delete that edge, this tree will actually be divided into two components. Okay, because there is exactly one edge, and therefore there is exactly one path between u and v, because in a tree between any two vertices you can have only exactly one path. So when you delete that path or delete that edge, what happens? The tree will become disconnected. Okay, I hope it is clear. And if you look at these two components are actually trees, right? These two components are actually trees by themselves, because this component is connected. Okay, this component is also connected, because they are not deleted any edge between any of the vertices there. So this graph is connected by itself, and this component is also connected by itself, and it will not have circuits. So it's a, these two are actually smaller trees. Okay, these two are actually smaller trees. Okay, suppose I call this component as T1 and this component as T2. Okay, and now can you tell me what will be the number of edges in this T1? Number of edges, and suppose T1 has n of T1 vertices, and suppose T2 has n of T2 vertices. So what will be the number of edges in this component? Since we have assumed by induction all the trees with up till n vertices has n minus 1, up till k vertices has k minus 1 edges. Okay, this component n of T1 will have anyway less than k vertices, so it will have how many edges? It will have n of T1 minus 1 edges. Okay, I hope it is clear. Why? We have assumed that for all trees up with k vertices, up till k vertices, it will have k minus 1 edges. So anyway, suppose your k is 100. So this cannot have more than 100 vertices, because it's a part of that original graph. So it may have some 70 vertices. So that means the number of edges it can have is actually only 70 minus 1. Okay, and similarly the second component also has less than k vertices. So since this is also a tree, it will have n of T2 minus 1 vertices. Okay, so these are the number of edges in both components. And how many edges would have our tree have? Our tree actually had k plus 1 vertices. Our tree actually had k plus 1 vertices. Okay, how many edges will it have now? It will have actually n of T1 minus 1 plus n of T2 minus 1 plus our deleted edge. Okay, how many, sir? N of T1 minus 1 plus n of T2 minus 1 plus our deleted edge. Okay, and how many exactly is this? How much is this actually? This is actually n of T1 minus 1 plus n of T2 minus 1 is actually, so we had n of T1 plus n of T2. So when you take n of T1 plus n of T2, you will get the number of vertices in actually. So this is actually n of T1 plus n of T2 minus 1. Okay, so what is n of T1 plus n of T2? That will actually be the total number of vertices in this original graphic, because we have not deleted any vertex. Okay, we have not deleted any vertex. So n of T1 will actually be number of vertices in T1 will actually be the number of vertices in the original graph will actually be the number of vertices in this component plus the number of vertices in this component, right? Okay, so n of t1 plus n of t2 will actually give you the total number of vertices in t, that is actually n of t or your k plus 1. So this is actually k plus 1, right? Okay, minus 1 means you are getting k. So when your tree had k plus 1 vertices, you had k edges. Okay, I hope it is clear. Okay, so how was the proof again? Tell me once again. So we had a tree there, and there was if I took an edge here, suppose UV, and there were some portions like this. Okay, and I deleted this edge. I am only deleting this edge. Remember that I am not deleting vertex. I am just deleting that edge only. So I'll be getting two components containing u here and another component containing v here, and this component, suppose it is contains only n of t1 vertices, and this component contains n of t2 vertices. Okay, so total how many vertices are there on the original graph? That is n of t1 plus n of t2 vertices are actually there. That is actually your total number of vertices, which is actually k plus 1. So this many vertices are there actually. Okay, now if I look at these two components, suppose I am looking at these two components, how many edges would be there in this component? By induction assumption, I should have n of t1 minus 1 edges in this set and n of t2 minus 1 edges in this set also. So how many edges would our original graph have? It will have n of t1 minus 1 plus n of t2 minus 1 plus this deleted edge also would be there. So you should give a factor of 1 also there. So in total it is n of t1 plus n of t2 minus 1. This is actually a total number of vertices in the graph, k plus 1 minus 1, so you will be getting k edges. So when you have k plus 1 edges also, you will have k plus 1 vertices also, you will have k edges. So your induction is hypothesis is true, therefore the result is true for all integers, positive integers. Okay, so what is it? When your vertex tree has n vertices, it should have n minus 1 edges. So this is the proof here. You can go through the proof, you can see the idea here. When I delete this graph here, this portion here, when I delete it, we can see that the graph will become disconnected. This is true for all trees. For example, I have taken a tree here and I have deleted this vertex here. If I delete this vertex here, this edge here, I will be getting two disconnected components. But if there is a circuit, if it's not a tree, so it is not necessary that when you delete an edge, it will be disconnected. For example, if you look at a graph here, this is not a tree actually, it has a circuit. So if I just delete this E, it need not be true that it has disconnected the graph is still connected. But in a tree, if you disconnect any edge, it will become disconnected. That's the property. So it's a basic bare minimum in the case of a tree. Okay, so if you delete any edge from a tree, it will become disconnected. Okay, so we have used that idea and induction also to prove this result. Okay, and moving forward, reverse one also, that is any connected graph with n vertices and n minus 1 edges is a tree. Okay, the reverse problem. So earlier it was, if a tree you will have n minus 1 edges. The reverse problem is when a connected graph, it has, suppose it has n edges, n vertices and n minus 1 edges, then it is a tree. Okay, so how will you prove that? So first of all, you have to show that it's a tree. Okay, so you have to show that it is connected and plus it has no circuits. Already it is shown that it is given to you that it is connected. We have to show that there are no circuits. Okay, suppose there are circuits are there. Okay, suppose there are circuits are there. I am assuming that the graph has n vertices and suppose it also has n minus 1 edges, and assuming that it has a circuit. Okay, so if you have a circuit, what you have to do is that you delete one edge from that circuit. You just delete one edge from the circuit. Okay, so when you delete that one edge, the graph will not be connected, will not be disconnected, because you are just deleting it from the circuit. So there are other ways to go from one vertex to another, so the graph will not be disconnected. So suppose for example is like this. Suppose this is the graph here. It's a very simple example. I am just deleting this edge, still this graph will be connected only. So when you have a circuit, so I am assuming that the graph has circuits. So you take one circuit there, so it can have many circuits, I don't know. So you take one circuit and you just delete one edge from that circuit. Okay, so that means the graph is still connected. Okay, and look at if the number of circuits has so if the circuits are over, stop it there. So if there are more than one circuit, go to the second circuit, delete one edge. Okay, then also the graph would be connected, because it's a circuit, it does not, so there are other ways to go around the circuit. So basically if I delete this edge, still, so suppose there was a vertex like this, suppose there was an edge D, vertex D here, so there was a path from this C to this D through this way. If I delete this edge, still I can go from C to D through A. This way also I can go from C to D. So deletion of one edge from a circuit does not disconnect the graph. That is the basic idea you have to know. Okay, so if there is one circuit, you delete one edge from the graph. Okay, so delete one edge from the circuit so that the graph is not disconnected. And if there are more circuits, again you delete one edge from the next circuit. Okay, so like that you delete one edge from all the circuits. So now so that the resultant graph is now circuit free and is also connected. Okay, so you are assuming that the graph has circuits. What I am going to do is that I am going to delete one edge from all the circuits, so that the resultant graph is connected and circuit free, or the resultant graph is tree. Okay, so I am going to delete one edge from all the circuits so that the resultant graph is a tree. Okay, such a tree is also called a spanning tree if you want to know. A spanning tree is basically a subgraph which is a tree and which contains all the vertices and is also connected. So basically, just for your information, it's also called a spanning tree. Okay, so this is how I'm going to construct tree from the given graph. Okay, now this tree, since we are only deleted the edges, we have not deleted the vertex, it should have n vertices. Okay, and the number of edges of this tree will actually be strictly less than n minus 1. Okay, so the number of edges of this result, suppose this graph is G and the resultant tree's graph is actually T. So the number of vertices of this T should actually be strictly less than n minus 1. Why? Because this T is obtained from G by successively deleting edges from a circuit. So basically there will be less number of edges in the tree rather than the given graph. Okay, but you know that, so you know that in a tree with n vertices it should have n minus 1 edges. We have just proved it. Okay, so we are getting a absurd result that n minus 1 is strictly less than n minus 1. Why? The number of edges in the graph is actually greater than the number of edges in the tree, but the number of edges in the graph was actually only n minus 1 according to our given result, and hence that will strictly be greater than number of edges in the tree which we got, which is n minus 1. This is a contradiction. So our assumption is wrong. What was our assumption? Our assumption was the graph contained circuits. So there was no circuits in the graph and hence it is a tree. Okay, so it's very simple, straightforward, not straightforward, but it's a very simple proof. What is the proof? The graph with connected graph with n vertices and n minus one edges is actually a tree. So the only assumption you have to make here is that you assume that it has, so in order to prove that it's a tree, you have to show that there are no circuits. So I'm going to assume that there are circuits. Okay, and if there are circuits, we can construct a tree by successively deleting edges from the graph. Okay, it will not disconnect the graph. Okay, once you get a tree like that, it will still have n vertices and it should have n minus 1 edges, but this number of edges should actually be less than the original number of edges, which was n minus 1, but that is not possible because both you will be getting both the number of edges are just the same. Hence our assumption that there was a circuit is wrong. There cannot be any circuits, so it is a tree. So these are very simple proofs. They can ask you all these proofs for exam. Please go through them. Okay, we'll again encounter some more properties in the next session. Okay, thank you.